Hello all. Thank you for joining us today. We're happy to have you. Thank you for sticking around to session 6 of the ALCF Intro to AI-driven Science on Supercomputers. Today, we'll be hearing from Sam Foreman, who's a computational scientist at ALCF, and we're going to start scaling things a little bit more. So Sam's going to share more about parallel processes and how to parallelize AI, which ultimately is extremely important anytime you're trying to scale anything in any capacity. So Sam, I'll hand things over to you and your Tetris. I'll let you introduce yourself and give a little bit of background, and then we can get going from there.
Sure. Yeah, it's actually playable too. Oh, whoops. Yeah, you can move them around, slide them down, kind of fun. Anyway, yeah. So thanks, Paige, for the introduction. My name's Sam Foreman. I'm a computational scientist here at ALCF. Yeah, so my background was actually in high energy physics. So I got my PhD in like lattice QCD, high energy theory. And since that turned into a postdoc at ALCF, and since then I've joined as a staff scientist and work broadly on scaling large language models mostly at the moment. But in general, I work with application teams to help them scale their application codes. And so that's what I'll be talking about today. So the topic of the talk today is on parallel training methods. Started. So here are a couple links. I think I also included them in the Slack channel as well. So hopefully everybody should have it. So the slides are online. And then the hands-on portion is contained in a README in the Argonne GitHub repo. So before we get started, I'll talk a bit about what we are going to cover today. So I'm going to start with a very general overview of the general thought process behind scaling a machine learning application, how you go from running it on a single GPU to multiple GPUs effectively, and then how to scale beyond just a few GPUs to up to many hundreds or even thousands, as the case for large language models. And so starting from very basic, starting on a single GPU, how to scale up, why it is advantageous, and what we get out of using distributed training. Then we'll start to see when that kind of breaks down, and when you need to resort to strategies beyond just typical data parallelism. And then I'll talk a bit about how this works within the context of large language model development and training. And then we'll spend the rest of the time on a little interactive hands-on demo that will train from scratch a large language model to talk like Shakespeare. Right, so getting started. So what is the big idea behind scaling? Or just distributed training more generally, is that we want to typically minimize the cost. So that's could be either in just time or as is often the case when you're dealing with GPUs, is actually converts into money. So if you're renting these things, which a lot of people do, luckily for us at ALCF, we have them on premises. So it's a bit of a different situation, but a lot of times the amount of time you run on your GPU ultimately costs money. And so you typically want to reduce the amount of time spent training. And the most straightforward way to do that is to maximize your application's performance. So if you know that your application performs well, then you're not wasting a lot of flop cycles. And that's typically the spot you want to be in. And so, as I'm sure people have heard and seen, this is particularly true when dealing with training large language models, when the cost of training can be on the order of many thousands of GPU months or weeks. And so really having a good understanding of how your application performs, how to get better performance out of it, are things that are actually very useful. There's this little link here from this Hugging Face has some good documentation. on general performance issues and how to overcome them to scale more efficiently. And so this is actually a pretty good read if people are interested in kind of more of a high level overview. But so how does this training process typically go? So usually, if you, for example, only have access to a single GPU or you're in the prototyping phase of your application, the easiest way to get started is to just run your model or your application on a single GPU. And so how this typically looks is you have some data that's broken up into batches that gets served sequentially into your network. So for example, X0 in this case goes into my network. I get some output. From that output, I'm able to compute a loss. From the gradients of that loss calculation, I can update the weights in my neural network and then feed in the next batch of data, right? So start with X0, forward back, you do a forward pass, get your loss, do a backwards pass, update your weights, and then move on to the next batch of data. And so this is the standard way of training if you're only on a single GPU. Unfortunately, as I'm sure people can tell, this is obviously not the best way you could possibly train. So if you're on a single GPU, that is what it is. But ultimately, this technique, if you want to, for example, scale your model size beyond what can fit in the GPU memory, then you're kind of out of luck. And typically, so like in the nodes and the resources at ALCF, for example, it's uncommon that you'll find just a single isolated GPU sitting by itself. The more common situation is where you have multiple GPUs co-located on a single node. So for example, on Sophia, I believe we have 8 GPUs per node. Polaris, there are 4, and Aurora, there are 6. And so typically what's the case is you'll have multiple of these GPUs located within a single node. And so what you then want to do is find a way to take advantage of all of the GPUs simultaneously. And so the most straightforward mechanism for doing that is using what's called data parallel training. And this is probably the most straightforward and easiest to understand approach. And so in this approach, what you do is put a copy of your neural network on each of an identical copy of your neural network on each of your GPUs, and feed to each of your GPUs a unique batch of data at each step. And so this is called data parallel because obviously we're parallelizing over our data. So each batch that we saw previously going into a single one of these GPUs, we then send it to each of them in parallel. And so in doing this, GPU, for example, would get as input X0, calculate its local loss value. GPU 1 would take as input X1 and compute its local loss value, and so on and so on. And so this is a very minor modification to our previous approach that now allows us to automatically take advantage of all of the GPUs available. And to be honest, this is actually about 90% of the way there. The only additional step you need to worry about is how to so right now this is everything is locally contained on a single GPU, but really we want to have some sort of global mechanism for averaging these losses and then using those averaged gradients to update the weights on all of our GPUs simultaneously. So how this would be done, for example, we can do the forward pass on each of our GPUs with respect to the local data that we see. Once we've completed the forward pass on each of our GPUs, we can average all of the gradients across each GPU. So in this case, that gives us, 1/n, the gradients from this loss plus 1/n times the gradients from this loss, and so on and so on. And if I have a mechanism for averaging these over all of my GPUs, I can then use those to determine a global value of the weight updates. Once I have a global value of the weight updates, I can then send those back to each of our neural networks and be sure that at each step, we maintain identical copies of the neural network. Because really what we're doing is essentially replicating multiple identical copies of our neural network. And then at each step feeding those identical neural networks unique batches of data, they will each output unique values of the loss. And so that allows us to actually just, train over all of these distinct batches simultaneously, as long as we have a mechanism for doing this kind of global average of the gradients, and then using that global average to then broadcast or to then update our weights on each of the networks separately. And so hopefully this is somewhat straightforward. It really is pretty straightforward. It really is pretty straightforward, even if you look at the details of the code. And there are a lot of different frameworks or libraries that will take care of the bulk of this work for you. So PyTorch's distributed data parallel library, for example, is probably the most common distributed data parallel implementation. And it's nice in the sense that it essentially just wraps your single GPU model and then abstracts away all of the, global averaging and updating, which is nice. And so it allows you to take a model that already runs on a single GPU, wrap it with this very simple DDP wrapper, and automatically kind of be able to take advantage of all of the available GPUs that you have, at your disposal. There's also another kind of similarly oriented library from Microsoft that's called DeepSpeed. It's a bit more. I've gotten asked a lot about how it's different from DDP. And I would say that at least how I think about them typically is that DDP is kind of a bare bones, very simple, does what it needs to implementation, and works well, and is easy to get started and get going with. Whereas Microsoft's DeepSpeed is typically more feature focused and has a lot more, kind of knobs and things that are useful actually, but can be overwhelming if you're not familiar, and just trying to get started. It can be overwhelming. So if you're interested and would like to take advantage of some additional features that DeepSpeed has, definitely worth looking at. And I'll talk a bit more about them in a couple later slides, but just to kind of lay the groundwork. When doing this distributed data parallel approach, one thing that is kind of important to keep in mind is that this averaging of the gradient step requires global communication. So that means that each individual GPU, or rank as they're commonly called, must participate in this communication call. And so that will only proceed as quickly as your slowest worker. So it is often the case that when this is actually happening in practice, each of these GPUs will be running at slightly different speeds. One GPU might be slightly ahead of the others, for example. And then it's very common that one of them might, kind of start to kind of straggle behind or get hung up on something. And if that happens, if you have one of your individual GPUs kind of lagging behind or failing to participate in this global communication call, then what happens is that everybody else basically is just waiting for your straggler to participate. And that can lead to a lot of hangs and crashing of jobs, especially when running at larger scales. So you can imagine if I were doing this across, 50,000 GPUs, and I know that one of them fails on average, every, I don't know, 100 hours or so, maybe. You can kind of get a rough feel for the statistics that efficient and effective global communication actually can be a major bottleneck when looking at very large scale distributed training. And so it's just kind of something to keep in mind. So this is what I was.
One question.
Please,
We have a
please.
question in Slack before you move on. Alfred asked, why are gradients across multiple GPUs averaged and not summed?
Yeah, so I in so I mean they're really the same thing. If you average them versus sum them, they only differ by a multiplicative factor. So the averaged version of the gradients would have a 1 over n factor in front. Um, yeah, I guess typically I guess kind of just thinking about it, you would want to average them because you would want the update that you then send back out to your networks to be representative of any individual whatever the data I saw on one individual GPU is. And so by averaging it across all of them, that kind of gives me a representative average of the gradients across all of my GPUs. Also, typically um, the the weight updates are actually dependent on the numerical value of the gradient. So the most straightforward weight update schedule, like momentum, gradient descent or whatever, uses the learning rate times the gradient essentially. And so if you have very large gradients, which would be the case if you typically sum them across all of your GPUs, that could force you to take a large step, which typically isn't. It's usually better to take multiple small steps when you're on this kind of stochastic convergence path. Then if you're trying to like find the bottom of a bowl, for example, and at each step you consistently like jump across the whole bowl, it'll be very hard for you to ever actually find the minimum. And so if you're always consistently taking large steps, which would be the case if you have large gradients that are used in your updates, then it's very possible that you would always be consistently taking very large steps, which would then just make it harder to find the actual global minimum.
Mm.
But I think averaging is just what's typically done. You can pretty easily imagine other cases where you might want to have more gradient information and so on. But it's kind of just a matter, rule of thumb usually.
Mhm. Cool. One other question. Yulene asks, how big can your neural network on a GPU on Sophia be, for example? So how many parameters?
Right.
And could you potentially adjust the learning rate by like n number of GPUs?
Yeah, so the on Sophia, so on Sophia is a bit interesting actually because I think there are 24 nodes total. 22 of them are standard issue 40 gigabyte A1 40 gig A100s, but there are two nodes that belong to this like big memory queue because those two nodes each have 80 gigabyte A100s. And so if you have an 80 gig A100, then you could obviously fit twice as large of a model as you could on a 40 gig A100. What the actual largest model size you can fit on an A100 40 gig? There's some like rough back of the napkin calculation that allows you to do it, but I can't remember what the formula is right now. I think it's something like 12 times the number of parameters in billions or something. I don't know. I know that on the 40 gig nodes on Polaris, for example, we can fit a variation on the 7 billion parameter Llama 3 architecture on a single GPU. But that's using half precision, as well as some other kind of memory saving techniques. But that even with all of that, in force, that's about right at the memory capacity. So I would say about maybe 7 billion parameters or so, roughly, give or take a few billion, maybe.
A question that was sort of a follow-up to Alfred's question is if your model can fit on a single GPU, you wouldn't average, would you? Or like, I guess, how would gradient averaging work if you were working just within a single GPU?
So if you're just in a single GPU, then okay, that's a good point. So the gradients that I would get out from a single GPU, if I have, 10,000 GPUs, that should be statistically equivalent to the average of the gradients across the other, 999,000 or whatever. And so so that's actually another argument for why averaging is actually the correct approach. Because in the limit, right, if you have in the limit of infinitely many GPUs, you would want the update at each step to, approach whatever it was on a single GPU. So in theory, this data parallel approach should be exactly, running on two GPUs.
We have a new friend.
So they normally eat, or they normally I ate at 4 previously, but now daylight savings this weekend. So they're really looking for their food earlier and earlier these days. So I hope he will cooperate. Anyway, yes, and so the idea being that you want this approach to be a true generalization of what it's like training on a single GPU, and you want all of the limits to agree, right? In the example where I train on 2 GPUs, versus, on 1 GPU for twice as long, I should get the exact same answer at the end of the day. And so the only way that I can really ensure that at any given step, my updates are of the same magnitude as they would be on a single GPU, they would need to be averaged over all of them, essentially. But I think there are probably some arguments to be made about, how that, what types of trade-offs there might be in that. But yeah, I'd have to maybe think a bit about it more. And I'd be happy to follow up on Slack too if people have other questions. But hopefully that answers it, kind of.
I think it'll work for now.
Cool. Okay. Yes, and so then now that we kind of have a general idea of how we could, train in parallel over all of our GPUs at the same time, we need a mechanism for actually doing it. So in particular, we need some mechanism for getting the gradients from each of these, from each of my ranks, performing some operation on them, and then sending that result back out to everybody, as well as a mechanism for taking something from one individual GPU. So for example, when I update the weights, these would all be locally stored on a single GPU. And then in order to send them to everybody, I would need a mechanism for, broadcasting them, sending them out back from one GPU back to everybody else. And so that is where communication libraries come in. So in particular, there are now, I guess, a few different communication libraries in Python that you can use. So MPI4Py is probably the, I would say maybe oldest, and is based on so it's a Python API to an underlying MPI runtime environment. So on Polaris or Aurora, for example, MPI4Py basically provides a Python interface to the mpitch library, versus on Sophia, for example, provides a Python interface to like the OpenMPI runtime. Similarly, there is a mechanism for doing distributed communication in PyTorch directly. So PyTorch has this distributed torch.distributed library, that contains mechanisms for all of these different communication operations that we will see. And typically these are then at an even lower level. All of this is built upon some vendor or hardware specific collective communication library. So on CUDA GPUs, NVIDIA GPUs, for example, they will use what's called the NVIDIA collective. Right, so on NVIDIA GPUs or CUDA GPUs specifically, they will typically use the NVIDIA collective communications library, which is commonly called NCCL. And on Aurora, for example, there is the Intel One API collective communications library, abbreviated as 1CCL. And there are links here for people who are interested to read more about them. One thing that's kind of important to keep in mind, which is what I was actually kind of alluding to earlier, is that these collective operations have to be called individually on each rank, and that means that each rank must then participate in the collective communication operation. And so if for whatever reason one of your ranks is straggling behind or gets hung up on something, all of the rest of them will kind of just be sitting there twiddling their thumbs, waiting for one of them to join. And then if eventually that last rank never actually joins, there's usually a timeout. So after like, I don't know, 30 minutes or so of waiting, if there's still no update, then eventually all of the rest of the GPUs will just give up and then your job will die. And so this happens more than I'm sure most of us, more than I would like, more than any of us would like to see. But it's, there are so many contributing factors to an individual GPU's performance that it is almost inevitable, especially at very large scales. And so there's actually a lot of ongoing research now into fault tolerant or kind of resilient communication and distributed training approaches that maybe I'll have time to talk about at the end if we get there. And so what are some examples of these operations? So maybe the most common, and this is actually what is used for the gradient averaging in particular, is called the all-reduce operation. And so the all-reduce performs reductions, some reduction, either sum, min, max, on some data across all of your ranks, and then sends that result back out to everyone. So in this example here, for example, we see each rank has some unique, x0, x1, x2. I can call this global all reduce. And for example, if I want to take the sum over all of them, I can call this all reduce with the sum operation, calculate this, sum over over the data on each of the individual ranks, get some output, and then send that output back to everyone. And so this is convenient for, as we saw previously, if you have a different loss value on each of your GPUs, and I want to have some global average of the gradient information, I can do an all reduce on all of my gradients, get the average gradient, and then broadcast that back out to everyone else. There's a more kind of specialized, and so you can imagine, instead of sending this result back out to everyone collectively, I can imagine just sending it to an individual GPU. And so that's called just a general reduce instead of an all reduce. So all reduce sends it out to everyone, to all of the workers, and the reduce just sends it out to an individual worker. So in this case, for example, you can see we reduce over this vector X and send the result to rank 2. In PyTorch and MPI, for example, there's also typically an argument that allows you to specify what operation you want to do specifically. The details are, very well documented in the either MPI for Pi or the torch.distributed documentation. Another very common collective operation is what's called the broadcast. So in this case, you have some data on one of your ranks that you want to send out to everyone. So this is common, for example, when you want to load in from a checkpoint or restart a training run. So typically what you will do is load your checkpoint only on a single GPU. And then once you've loaded it in successfully on a single rank, you then broadcast out the model and the optimizer states to everyone. And this is typically a better approach than trying to have all of them read from the same checkpoint simultaneously, because that can lead to race conditions. If you have multiple threads trying to read from a file at the exact same time, that can lead to these race conditions and file locks and ultimately cause your job to crash, which again is not what we want to do. And so the typical way, actually, whenever you want to do file IO, generally the best way of doing it is doing it only on a specific rank, loading in what you need only into a single GPU, and then sending whatever it is that you need back out to everyone. And so that just helps prevent like race conditions and multiple workers trying to read from the same file at the same time. Another pretty common collective operation is this all gather. And so this is kind of maybe similar to the all reduce, where each rank has some unique data locally. And in this all gather, then what we do is basically gather the data from all of the ranks and send that out to everyone. So in contrast to the all reduce, where we do some inner operation here, and then get an output and send that output, this basically just concatenates the input from each of the different ranks into a list and sends that out to everyone.
Sam, we have a couple clarifying questions.
Please.
One is sort of just like confirming, like, what are ranks, quote unquote?
Yes.
Is this referring, in this case, is it referring to the GPUs being used?
Yeah, so in distributed or parallel processing, typically so a rank is like an individual worker. Typically for machine learning or AI training, you typically assign one rank to each GPU. So rank 0 would be GPU 0, GPU 1, GPU 2. And that's for about 90% of the use cases, you can automatically form that association that rank corresponds to GPU. But historically that wasn't always the case. And so a lot of parallel processing would rely on multiple threads or multiple CPU cores, for example. And then in that case, if you only have one CPU with 6 cores, then I can assign one rank to each core of my CPU and then kind of run all of that, following all of the same parallelism strategies that we've seen previously. It basically just doesn't need to be a GPU. Most commonly, it will refer to an individual GPU, but that's not always the case. So it could also, kind of be used you could I could imagine that there would be a case where rank 0 would be a CPU, rank 1 would be a GPU. You could even imagine, like, with the increase in popularity of these AI accelerators, even one rank could lie on a Cerebrus chip. And so rank is typically used because it's more, it's a generic term for a computing device. Typically these days it corresponds to a GPU, but not necessarily. Hopefully that.
Yeah.
Two maybe, yeah.
Cool.
If I could go a little further on that, if you're doing something like I think pipeline parallelism and you're using like 2 separate GPUs and you're pushing them, like you have separate layers on them and you need to run them sequentially, would they be considered one rank or would it still be 2 ranks that you're using?
That's a good question. And that is jumping ahead a bit, but that's okay. So yeah, the question was about, so there's, as people saw, we skipped a few slides in here. But there are other parallelism strategies. So data parallel is the most, naive, straightforward, but as you can imagine, there are plenty of other parallelism strategies. And so the question specifically was about this pipeline parallelism strategy. And so in pipeline parallelism, typically what you do is kind of just break it down how it's shown here on the right. So you put some subset of your layers on one GPU, and then, kind of forms this pipeline that works through vertically through each layer. And so in this case, the rank would still correspond to GPU 0 because this is actually the device that does the communication. Yeah, you typically want to assign ranks to the devices that will participate in your collective communication calls. But the distinction for how your model gets split up across devices can be non-trivial, and so it's actually yeah, I would imagine very easy to get these types of things confused. Yeah, but typically you want to assign ranks to the devices that will be participating in the communication calls. Does that answer it, hopefully?
Yeah, all right, thank you.
Yep, yeah, no problem. And through all of this, please, if other people have questions, please feel free to interrupt. Yeah, as I'm sure people can see, I'm not actively watching Slack.
One other question, a clarification, why would you want to use reduce and not all reduce? Going back a couple slides.
So yeah, whoa. So yeah, it's maybe a bit less, I would say probably less frequently used than I'll reduce. So you can imagine if you have one rank that it wants to do some graphing, or you want to like make some plots or something, for example, you can imagine getting, instead of sending it out to everybody, I only need it on one individual rank. Then that prevents having multiple duplicate copies, otherwise cluttering up the other GPUs. And so I know I only want to do my make my plot. Typically, you only want to do like graphing operations, plotting, those types of things from one worker as well. And so this would provide you a mechanism for getting some global notion of data, and having it only on a single rank. But yeah, you're right. I mean, it's probably less generically applicable than like an all reduce.
Great, thank you.
No problem. Okay, yeah, so I guess this is probably where I was. So why do we want to do this? So, and how is it advantageous? So the most obvious advantage is that by having, n workers, each processing, each batch of data simultaneously, if I have a micro batch size of 1 on each GPU, and I have n copies of that basically scales the amount of data that I see at each step by a factor of n. So now previously if I were training on a single GPU, I would see at each iteration one batch go through. And so to reach 10, to get through 10 batches, for example, it would take 10 iterations. Versus if I were to train that on 2 GPUs, then I would at each iteration see 2 micro batches, and so it would only take 5 steps to get through the same amount of data. And so on and so on. You can imagine, scaling up, going from 1 to 2, going from a single GPU to 2 GPUs, you cut your amount of time, or you cut the amount of steps you need in half. And so you can get pretty big, you can get a pretty big advantage out of that, just, straight parallelizing scheme. There are a couple more subtleties associated with distributed training, so it's maybe not always exactly as straightforward as just scaling. So there are a couple other things maybe to keep in mind. So typically another thing that is done is that the learning rate is scaled by some factor proportional to the number of GPUs. So you'll commonly see the learning rate being scaled as like the square root. Sometimes people just do it as proportional to the number of GPUs. And this has so each global gradient average will have less information than any one of them individually. And so by scaling this learning rate according to the number of GPUs, I kind of account for that trade-off. But there are some other kind of knobs in here that you can try to change to exactly match the performance and behavior that you see on a single GPU. And yeah, there's actually there's actually an interesting link that has some good examples of how large batch training impacts the dynamics of how large batch training with large batch sizes can impact the dynamics of training. The most glaring, obvious speed up. So this is just taking the amount of time required to reach 75% accuracy on ImageNet. And so this is kind of not fair comparison because they were using different GPUs, and B100s are much more powerful than P100s. But everything else kind of being the same, going from 8 GPUs where it took about 100,000 seconds, scaling that up just, straight up to 2048, I can reduce the amount of time by, I don't know, I think that's a very large factor, and achieve the same overall accuracy in a significantly less time. And so this is kind of the big idea, right? If I can split up my work across more workers, I can get it done in less time. Okay, so as I said before too, you really do want to be sure that at each training step, each worker is always going to receive a unique batch of data. There are two common ways of doing this. I would say the most common is to manually partition the data ahead of time. So, split it up explicitly, ensure that, each worker only has access to its local copy. And then in doing so, you're, making that explicit. And that's generally the more recommended approach, I would say. Another way you can do it, that's maybe a bit more naive, but maybe easier to implement, would be to just, from each worker, randomly select a mini batch. In this case, then each worker would be able to see the full data set. And this is probably not recommended typically because there's a small, some finite chance that I will randomly select data that has some overlap. And so in that case, that's not really advantageous. But it's maybe a bit easier to implement. So you also kind of see it done sometimes in practice. This, I guess I talked about previously when I talked about the broadcast operation. So yeah, typically when you're loading from a checkpoint or restarting training, typically what you do is only load the checkpoint on a single worker on a single GPU. Once that's loaded in, then you can broadcast, for example, like the model and optimizer states back out to everyone. Best practice, so I'll, for the sake of time, probably skip this. So that kind of takes us to the limits of distributed data parallelism. And if your model is, if you have your model and it fits on a single GPU and that's as large as you ever want to make it, then I can just use distributed data parallel and never have to worry about anything else. But typically you will eventually reach some, wall. Either you want to get better performance out of your model, and the way to do that is to scale it up. And then eventually you'll scale it up to the point where it no longer fits on a single GPU. And then at that point, your life is much harder. And so then if your model, eventually scales up and no longer is too large to then fit on a single GPU, the easiest approach at that point would be to use one of these offloading kind of wrapping libraries. So there's this zero offloading from Microsoft DeepSpeed, which was, I think, kind of the first implementation of this like offloading strategy. And then PyTorch pretty quickly copied it and implemented it in PyTorch native and called it fully sharded data parallel. So this FSDP. And these are nice because they require pretty minor modifications to your existing. So if you have a distributed data parallel implementation working, it's very easy to go from distributed data parallel to either zero or FSDP with just kind of a couple additional settings. And then that will actually get you pretty far. So you can really free up a lot of memory with either of these two approaches. If that still isn't enough, then ultimately you'll eventually need to resort to some additional parallelism strategy. So the most common approach, or the most popular, I would say probably, is to use deep speed zero offloading. So this is a really actually very convenient approach that you can take advantage of if your code is using deep speed. And there are kind of three settings that you can set for this zero offloading. With each increasing zero stage, you free up more memory. So I can fit a larger model with zero stage 2 than I could with zero stage 1, and a larger model then with 3 than I could with 2 than I could with 1. And how this works behind the scenes. So in typical distributed data parallel training, each GPU retains a full, entire, complete copy of the model parameters, so shown here in blue, as well as the gradients for each individual step, as well as the optimizer state for each individual parameter. And so each GPU has redundant copies of all of this information, which is kind of unnecessary, right? Each GPU doesn't need to have, if I know that my neighbor has this slice, for example, then I don't need to hang on to it anymore. Anytime I need it, I can just grab it from him. And so what this does then, with increasing zero stage, basically retains on each GPU only what is needed for that GPU's calculations to proceed. So with zero stage 1, you offload the optimizer states. So as you can see here, now each GPU only retains its local, its small portion of the total optimizer states. And then whenever it needs to, get some value that it doesn't have, it just, reaches out to its neighbor and says, hey, I need that, optimizer state, send it over, gets it, runs the calculation, and then offloads it again, frees up that memory. And so this comes at the cost of increasing computation. And so it will then thereby impact your throughput. But it's advantageous if you are out of memory and want to fit a larger model or a larger batch size. And you can increase the zero stage to free up more and more memory. This is a very complicated diagram that kind of more or less just says the same thing. And this is from PyTorch's FSDP library. But it kind of follows a similar strategy of being able to offload parameters, gradients, and optimizer states, either to host memory or to CPU memory. So these are kind of simple wrappers around what is otherwise normal distributed data parallel, and are pretty easy to take advantage of and require relatively minor modifications to an existing code. If you need to then go beyond that and really pull in additional parallelism strategies, you're kind of in a much harder place and will need to do that more or less yourself. So in general, there are no one-stop shop, libraries that will automatically take a model and distribute it across all of your GPUs. So in general, it's going to depend a lot on the specifics of your network. And so these types of parallelism strategies are much more involved typically and require pretty painstaking, manual specification of which tensors live on which devices, and so on and so on. So tensor parallelism specifically is notoriously difficult to get implemented correctly. And there's no kind of, standard way that will work for all different models. Pipeline parallelism, so we saw very briefly, and I'll touch on it again in a minute. There are now kind of somewhat native implementations in PyTorch and DeepSpeed. There's also sequence parallelism, so splitting your input and parallelizing across your sequences is a relatively kind of a hot topic of research at the moment, because sequence parallelism allows you to scale to very long context windows. So that allows, ChatGPT, for example, to have a very long working memory of your previous conversations and things. And so scaling out that context window is a, kind of highly desired, degree along which to scale. And so sequence parallelism is also, very active area of research that also usually requires manual implementation. If people are interested in this in more detail, we have this Megatron Deep Speed repo hosted at Argonne LCF that supports all of these parallelism strategies. And I'd be happy to talk more about that offline. So this was back to where we were before, this pipeline parallelism. So this is maybe the most straightforward of the other parallelism strategies to implement, because you can essentially you just split up your forward pass, break up your forward pass at different points and put different components onto different GPUs. So in this case, the full forward pass obviously would go through 0, 1, 2, 3, and then the output. And if all 4 layers, for example, are too large to fit on a single GPU, a very easy way to split it up would be to just put the first 2 on GPU 0, get the forward pass, go through 0, go through 1, get that output, and then send that output to the next GPU and continue on with the forward pass. And there are, so this is kind of increasingly, there are now ways to do this automatically, which is kind of nice. They're still, I would say, in early development stages, so there are bound to be some rough edges, but it's nice that there's now support for these parallelism strategies in PyTorch and DeepSpeed Native. The more complicated parallelism strategy would be what's called tensor parallelism. And so in this case, if even for example, a single layer is too large to fit on a single GPU, then you might need to split the layer up so only half of it is on GPU 0 and half of it on GPU 1. And then this is much more complicated, as you can kind of imagine, because in order to construct, to go through the forward pass and get through layer 0, I can only do some of the calculations on GPU 0, then I have to either send those to GPU 1 or get the missing weights on GPU 0. And so there's a lot of intermediate communication that needs to happen for these tensor parallelism strategies to work successfully and be efficient. And typically you would want to restrict this communication to only being within a single GPU. But again, the specifics are going to be very dependent on your application and so on. So here's a very, very simple example of how this could actually work in practice. So say, for example, we have just a very, very simple model, 3 weights. Each of the weights live on a different GPU. So as you can see, W0 is on GPU 0, so on and so on. And I want to compute the sum of each X component with the its corresponding weight. But each GPU only has a fraction of the total weights. So what you would do, GPU 0 gets as input X0. It has W0, so it can compute X0, W0, send that result out to GPU 1. GPU 1 can receive as input X1 and has this W1, so it can calculate this term, and then it receives this from GPU 1. Once it's got those 2 terms, it can then send those out to GPU 2, who receives X2 and has W2, and that at that point, then it has everything it needs to carry out the full calculation, and it can sum the previous 2 terms with that to get the full output. And so as you can imagine, this is probably the easiest, most straightforward example of how this could be done. In the real world, this is typically much more involved, and so you can kind of maybe get some sense for how that would be done. In the sake of time, I'll probably skip some of these, but the slides are here if people are really interested. So Paige, when I go till 4:10?
So actually, it'll be 4:15 today.
Oh, okay. Oh, cool.
So you probably have another about 20 minutes.
Okay, cool. Okay, cool.
Amazing.
In my head, I wasn't sure. I thought there was a chance that I was supposed to wrap up by 4. So then I was like, oh, really gonna be
Oh
pressing.
no, so much
Okay, cool.
time.
4:15. Okay, perfect. Yes, then maybe the one thing I did want to say that I skipped over. Is this slide on how to decide a parallelism strategy and how to know which approach to use when. So if you're on if you only have a single GPU, there's not really much you can do. There are some kind of experimental techniques that allow you to break down in like PyTorch, you can have this like sequential layer, sequential stack of layers. And so there's this implementation in deep speed that allows you to break up a sequential block and essentially just execute it step by step, loading each layer as needed onto the GPU, which is kind of nice. I think you see pretty poor performance, but at least there's a strategy in the event, if you only have a single GPU and have no other way to do it, there are ways to proceed. But if you, as is more common the case, you have at least a single node with multiple GPUs on that node. If your model fits on a single GPU, then it's straightforward. You just typically would want to use DDP. You could probably scale it up a bit further using zero offloading. But in the event that your model does not fit on a single GPU, then you kind of have to resort to either one of these additional parallelism strategies, so either pipeline or tensor parallelism, or really resort to offloading using kind of zero strategy from deep speed. And so again, this is very dependent on the connectivity between nodes, but typically pipeline parallelism is going to be faster than zero or tensor parallelism. Just because each step in the forward pass isn't going to require communication from the outside. And so it's typically a bit faster. But again, it's going to vary a lot depending on the connectivity that you have between nodes. So the next few slides are maybe high level about large language models, but you guys have seen all of this in the previous weeks and at least should now have a working understanding of what large language models are and kind of how they, function. So I'll probably skip some of this. Some funny slides. Yeah, this just kind of shows the explosion in architectures. So going back to 2018, and this is even a bit out of date now. If we were to actually include all the releases from 2024, there would be many, many, many more branches on here. And so this is really just shows the explosion in research interest in large language models, as well as some of the more popular current architectures and where they all kind of came from. Life cycle is not terribly important. Forward pass. So maybe just to make sure that I have enough time, I'll probably switch over to working through the hands-on section. Unless there are any other questions about anything I've talked about so far.
There's nothing in Slack right now, but if anybody has specific questions, feel free to unmute.
So you know what? I'm going to stop sharing that and share my terminal. Hopefully. There we go. Okay. I thought I would be clever and request a note ahead of time. So I am already on, as you can see, Sophia GPU 23. But if you are just coming from the login node, the first thing you would need to do is submit an interactive job. So this can be done with this queue sub, select your project allocation, select the appropriate queue, however many nodes for however long you want. But I did that ahead of time, so I wouldn't have to wait and risk the chance of not getting a node for this talk. The next thing you need to do, so once your interactive job starts and you get launched into the compute node, on Sophia, you need to set these proxy variables. So these are included in the hands-on example. Yeah, and so these are just these HTTP or proxy variables that allow you to connect to the outside world. So you need to be sure to set those, otherwise you won't be able to follow the rest of the instructions. And then just for, completeness, I'll do this just as you guys are now, so I'll work through it step by step. So I'm just going to make a temporary directory and then start with a completely fresh clone of everything. So the next step in the instructions are to clone. So the first repo we'll need to clone is this wordplay. It's called, which is just my personal fork of Andre Karpathy's NanoGPT repository. It has some additional features that I won't get into, but that's what it's based on and where it comes from. So clone that, navigate into it. Then we need to clone this library called Easy Peasy. That is just a little library that I write and maintain to help simplify my life a bit. That has some nice features specifically for working on the ALCF systems. So those are both cloned, and then you need to make sure that you are in this wordplay directory. And then once you've done that, the next step is to source this. So it's important to specify or to set the PBSO working directory to whatever directory you're currently in. Because some of the functions in this shell script will be defined relative to this path. So you need to make sure that that corresponds to the actual directory you're in. And then you want to source this utils.sh script that provides some nice helper functions. So the first one being this easy peasy setup Python. And so this will work on any of the ALCF systems. It will basically figure out which machine you're on. Depending on what machine you're on, it will then load the most recent Conda module. It will then look in your working directory for a virtual environment whose name matches that Conda module. If it can't find one, it will then automatically create one and being sure to match the name of the Conda module and then activate it. You can see now my current Python is this virtual environment built on top of the 2024-08-08 Conda module on Sophia. And so that sets up Python. And then the other thing we need to do is this easy peasy setup job, which basically just parses your your PBS node file. So really what it does, it counts the number of lines in here. And then, so each line in your PBS node file corresponds to an individual node. It then figures out how many GPUs are on each of those nodes. That information with the number of total nodes gives you the total number of GPUs. And then it saves that into your environment. So we can see, for example, am I on a single GPU? Yes. Oh, okay. All right. Never mind. I was confused for a second. So in this case, we're only on a single GPU. I thought I had more. I thought I requested 8, but I guess maybe not. At any rate, once you've done those two steps, the next thing you need to do is install these Python libraries. So pip install. I like to force this require virtual environment because then that just really ensures that the previous steps had worked correctly. Because then if you're not in a virtual environment, this will fail. And so it's just kind of, an additional check to make sure things are working how we expected or wanted them to. Hopefully this should go quickly. Then you need to, so that previous command installed easy peasy, and now we need to install this wordplay library. So a local or an editable install of my current working directory. again, requiring a virtual environment. So this will proceed and then install. Never as quickly as you would like it to, but here we are. And then you can check and make sure that everything is installed successfully and correctly by running this little easy peasy.test disk module. So it's a very simple DDP example with a really small network that I usually just use as a smoke test to make sure that everything is set up correctly. And we can launch it then with MPI run. So as you can see here, I guess, yeah, it only has one GPU. I thought I had grabbed 8 before this, but maybe not. In the event that you had 8 GPUs, this would, spit out using 8 of 8 available CUDA devices. And then it, just loads up a very simple 4-layer model, runs for like 100 steps or so, then makes some very simple plots of the iteration, time per step, forward, backward, and then like the loss and things. And so this is just a very simple smoke test to make sure that your distributed setup is all set up correctly and running. And then if you're able to get through that step correctly and successfully, the next step is to prepare the data we'll be using. So for this example, we will be using this Shakespeare character embedding data set, consisting of a little over 1 million characters, and it's just the works of Shakespeare all tokenized. And so once we've gotten that data prepared, the only thing left to do is then launch and run the training. And if this works, you will see that it will learn to talk like Shakespeare, hopefully. No, it won't. What? Or what happened? Let's see. Try again. I think I had a running process that was not killed or something successfully. Hopefully this will work. No. Yeah, no. Oh, duh. I was running experiments just before this talk, and that was not the command I wanted to use. Sorry. So hopefully like this one will work. Shakespeare. Oh, I see my issue. So I was in the previous example, I was specifying a Yelp data set, which doesn't exist, so it was crashing. Hopefully now this works in the next 4 minutes. Cool. Okay, at least got past that. Always gives you a bit of a slight heart attack when the example I was doing just before this doesn't work when I go to do it live. But luckily, I'm an expert debugger, so I figured it out. And so now this prints a bunch of information. It prints this nice legend that tells you what all of the abbreviations mean. And then it prints out this. So every so often it will do an evaluation. Basically just prompt the model and say, what is an LLM? And then print out the model's response. So as you can see here at the very beginning of training, before this 10th iteration, the output from the model, as you would expect, is just, all gibberish, just completely random string of characters. And then hopefully as the training proceeds, we should hopefully see it start to, learn to talk like Shakespeare. So you can even see, that going from that first evaluation to the second one, these are at least kind of maybe starting to look like words, not meaningful words, but a bit closer. Then you can see it kind of starts to use the, dialogue. Shakespeare loves it. And then as you continue to train, it should just get better and better. So this is I don't know, maybe not, maybe not completely groundbreaking or revolutionary example, but I think it's kind of, simple, easy to understand, makes sure that, if I were training my model on the Shakespeare data set and it was, learning to talk like, I don't know, somebody else, not Shakespeare, I would be very, that would point me to something being wrong in my implementation. And so this is really just a, kind of sanity check to make sure that the model is learning from the data that I'm providing it, and behaving in some sort of predictable manner, which is not always the case. And for people who do this day in and day out, you'll spend a lot of time chasing things down that you expect should behave one way that doesn't actually. And so there are a lot of very subtle failure mechanisms that can really, impact model performance and ultimately impact your model or negatively impact your model. And so there's a lot of moving parts, and making sure that they are all implemented correctly and working together correctly is a very non-trivial effort in most cases. So anything that you can do to confirm that your model behaves according to your intuition is usually advantageous. And so we can see here, after, where are we at, 2,500 steps or so, it's getting there. Kind of sounds a bit like Shakespeare, lady, all the names and so on. And it'll just, get better and better until it kind of is just repeating Shakespeare exactly. And so that was about all I had. So I don't know why here I only grabbed a single GPU, but if you were to rerun these steps, the exact same steps on a job with more than one GPU, everything should work the same, and it should automatically take advantage of all of your available GPUs. And so actually that brings me to the homework, which any sort of proof that you have ran this successfully, from a log, stamp log file or a weights and biases URL or something, so on, anything that kind of just shows that you were able to run it successfully. Maybe try a few different configurations, and then submit that is what I'll be looking for homework. And I'll make a note of that in the README on the GitHub as well.
And one other thing for homework, if folks are running on ALCF machines, I would recommend running on Sophia, in part because Sophia, while it's a smaller machine, is used significantly less than Polaris. And you might run into issues where you try to run something on Polaris and then your queue time is a week. So
Yep.
I would recommend jumping on Sophia. It's not used as much. If it's if you see that the queue time is going to be a little bit long, that maybe come back in a little bit at a different spot, a different time, just because it's generally not super used. So you all do have access to Polaris, and I would recommend running on Sophia.
Yeah, much faster turnaround usually on Sophia, definitely. And just maybe so that I don't look like a complete liar. This job now has 8 GPUs. And so if I were to my keyboard just is not working with me. There you go. So at least people can see when it runs on 8 GPUs. I don't know why I saw these errors earlier too. I'm not actually sure what's going on. But it seems like it proceeds anyway. Yeah, so that's about all I want to say then. Thanks everyone for listening, and feel free to hit me up independently if people have more questions. Be happy to talk more offline with anyone. And with that, I can give it up to Arvind.
It looks like, I don't know if Arvind's here yet. So I think if folks still have, if they have any specific questions right now, feel free to ask them either in Slack or unmute here. So I guess one question that someone just asked is, if they don't have access to an ALCF account. So like what could someone do if they don't necessarily have access to maybe a set of GPUs like they have on Sophia?
If you
Is there an
have
alternative
your,
there?
if you have a MacBook, you can run this across CPUs just as well. So this is on my local MacBook. I can use MPI run, launch across 2 of my, I think there are 12 on my machine. And so you can, it doesn't need to be on a GPU by any stretch of the imagination. So this gets back, as long as I didn't break anything internally. Yeah, so there's some disagreement. PyTorch doesn't like to use the Apple accelerator, like the Apple GPU. So there's some conflict in here, but if it weren't me doing this live, you should be able to run this on across 2 CPUs as well, using MPI run. So this should work. I don't know why exactly it doesn't now. But yeah, you can. So it obviously won't be as performant, obviously using CPUs instead of GPUs, but yeah, you definitely can. And I frequently test some of my like very simple distributed logic just on multiple, using 2 CPUs on my MacBook instead. Hopefully that answered it.
Yeah, I think that's a good alternative. Any other questions while we're waiting for a science speaker? I see someone typing in Slack. Folks can feel free to unmute as well if they want.
Please, I'm an open book. My dogs are sleeping now too. Easy.
Yulene just asked, can we change the input prompt during a run? So could you change, like, the prompt right now is what is an LLM? Could you change that?
Yeah, yeah, yes. I think I don't remember now. Exactly how I thought there was. So actually another thing you can do, to figure out all of the possible options, actually. You can Python 3, or I actually you can just, if you have it installed, you can word and this will print out a detailed list of all of the options. I can't remember now whether or not I put in a flag to allow you to override the like evaluation prompt. I thought so, but I might be misremembering. No, I'm looking, maybe not.
And we have one comment in the Zoom chat, just requesting to have sort of a clear step on how to do and submit the homework. And it sounds like you'll put that on the README.
Yeah, I will put an explicit note in the README on GitHub. But yeah, any sort of proof that you were able to run it successfully, will demonstrate that at least you followed along and were able to run it. Yeah, feel free to get creative. I didn't have time to talk about it. Is Arvind here yet?
No, Arvind.
I
One
don't want
question.
to keep talking if he's like.
Yeah. Keep on going.
So the other thing I was going to say, the other example is you can, so that previous example used the Shakespeare data set, but you can also, this works actually with any Hugging Face data set. So you can, another example I like to do is use this Yelp review data set. And so it's a bit larger data set. But if you do repeat the same process, you'll see that the evaluation eventually learns to, spits out like a whole bunch of, I don't know, the server and this and that, like it's a Yelp review, which is kind of funny. Yeah, so that's another example you can do. You can also, there's actually a lot of functionality that's not very well documented. And you wouldn't really know about it unless I were to bring it up right here. But you can also like load in the GPT checkpoints and kind of do a fine tuning run from the pre-trained weights from Hugging Face. There are variations on the llama architecture. I've got like flash attention implemented, a few other things. But if people have like thoughts, questions, comments, anything about either this like easy peasy library or this wordplay, I'd be more than happy to talk about it offline too.
Do you recommend using weights and biases? I've been thinking about setting up like a personal server.
So I love weights and biases. So I'm very biased. But I personally recommend using it. I just, if for no other reason than it's free and easy, and you you it is very useful to have a single source of truth that you can always refer to, because it's just much easier to go and look at graphs and weights and biases than trying to find some 2-week-old log file that's in some random directory that you can't remember, that you don't remember how things have changed since then. And so having weights and biases in place to obviously track metrics and track things, across experiments is a very useful functionality. But really just having being able to use weights and biases well and using it to effectively, it's a very powerful tool that really has saved me a lot of headaches and a lot of pain over the years. And so I strongly recommend it, and I am a big fan of it. I know not everybody is. I remember even before it came out, I was using TensorBoard and like manually, SSH tunneling through, Polaris login, connecting to my TensorBoard instance on the GPU node, having it stay alive only while my job is alive, spinning it up every time. So then to have weights and biases come along that provides it all in a web interface was, music to my ears. I was actually I think like in the first 500 users.
Wow.
And so I've been using weights and biases for a long time and I'm a big fan.
Well, thanks for the vouch. I'll check it out. I've seen it, but I saw it like years ago, and I never like thought of it. And I've just heard it's fantastic for like keeping logs of what you're doing for training runs.
Yeah, honestly, like there are so many different, like comparing against experiments, it automatically if you have like locally changed files in your working directory, if you made local changes to the code and then you run it, what it does, it actually creates a branch before every run, and so every run is exactly reproducible. You can always go back to the exact git state that run ran with, which is very convenient when you want to remember what you're doing 2 weeks ago and be sure that that change that you thought you implemented was actually in effect in that run. It keeps track of logs, configurations, all sorts of things. I could very easily spend another hour and a half talking about weights and biases. So I'd be more than happy to talk offline too if people have questions.
So still no Arvind. One question in the Zoom chat was like thinking about like alternative places that you could use. how would Google Colab be able to support this or not? Do you know?
Yeah, so I actually have a a collab example that runs through the Shakespeare. Runs through that exact Shakespeare example we just did, but only runs on a single GPU and runs in Colab. So there are notebooks here in this like wordplay notebooks that all should work on CP on Google Colab, no problem. So this was back in February. So things might have changed slightly since then, but with maybe just a little modification, I think it should all work on Colab out of the box. You'll only be able to use a single device, unfortunately, but
yeah, which is, I don't know, something important to sort of think about. Being able to compare the two. Well, I think looking at the time, since it's 28 past now, and respecting everybody else's time, I want to thank you, Sam, for the presentation and the hands-on today. I will follow up with, we have a recording of Arvind Ramanathan speaking previously about the work that he's doing in autonomous discovery that I can share.
So I think you've been seeing a lot of things that talk about AI and what can be done in the context of learning simple functions or simple ideas from what Kuyo was already describing. The context for why we are doing what we are doing in the lab, let me give you a little bit of history. So what I'm going to focus on is, say, how do we design new organisms or design life from scratch? And in that context, we are mostly interested in trying to see how we can design new proteins or new enzymes and new things that we can actually like bring to life in the context of biological systems. So mostly this is focused on this idea that we can bring together aspects of robotics, aspects of AI, and biology together to solve some interesting problems, from biomedical discoveries to like trying to understand, for example, how SARS-CoV-2 evolves. So one of the first applications that we actually did was that we built what are called as foundation models for genomic data. And these models are essentially like ChatGPT, very large models trained on huge amounts of genome scale data sets. And they were fine-tuned on SARS-CoV-2 genomes that are available, nearly about 1.5 million sequences from the first year alone. And then we decided that we should test the model in terms of like looking at the next few years worth of SARS-CoV-2 data and see if we can predict all the emerging variants. So for example, Delta, Omicron, Iota, Eta, Gamma, all these different things, just by looking at Alpha and Beta as these two main strains of data that were provided as training data. And in fact, one of the things that happened as a consequence of doing this, which basically took a lot of compute time on our systems, was that we actually got awarded what is called as the Gordon Bell Prize for high performance computing applications in COVID-19 research. And the ability to basically build these pre-trained transformer architectures for nucleotide data was actually kind of a big deal, because at the scale at which we are actually training, it would take at least a couple of weeks to train these models on the entire supercomputer. And we basically also showed that it is possible for us to observe nearly linear speeding on these models in order to make them converge in less than half a day, right? So if you were to take 2 weeks to train and converge these models on a supercomputer like Polaris, which has 2048 GPUs, it only took about 0.5 days to train it on the Cerebrus architecture. And by generally doing this, we were able to say we can predict these new variants that are out there, for example, even the BQ1 variant, which means that this model is actually able to like tackle real world cases. For example, if you want to predict new emergent cases of like SARS-CoV-2 or other viruses in the wild, for example, influenza variants, or you might be interested in doing, Zika virus or other sorts of variants that are important to kind of see. Now, how can I use this ChatGPT sort of idea? One thing that we do in the lab is to actually build experiments that allow us to, um, design new enzymes or new synthetic genes that we might be interested in doing. So this is actually an example where we can take these pre-trained large language models, use these models as sort of a reward function that can be rewarded through experimental data. So for example, I can say this protein expresses well in the lab, and therefore I'm going to assign it a bigger score. Or I can use some structural metrics from a prediction like AlphaFold. AlphaFold, if you have not heard, is this protein structure prediction algorithm that was built by Google DeepMind. And they were able to show that they're able to outperform any other structure prediction code out there, which is kind of cool that they're able to do this. But one of the things that we wanted to do was how do we take this to the next level of integrating these reward models and then generating new examples that kind of align with this idea that these are really new synthetic genes that have not been seen in the nature. So what you see on the right-hand side is this generated sequences that are shown in the colored dots here. And this is from the natural sequences that are shown in the grayscale. But what I want you to observe is this little corner on the top, because we were kind of like steering the model towards it. The model was steered in a way that could actually like generate new sequences that are not seen in any of these gray plots. And you can hone in on some of these plots and say, okay, can I select a few sequences and put them through this experimental data for predicting what the catalytic rate of that enzyme might look like in the wild. So when we did that, we can actually simulate that entire process. And one of the things that was really cool was the fact that when compared to the wild type, which is shown as the purple line here, which is called 5-MDH, it is from the bacteria called E. coli, which I'm sure you would have heard of. What you can see is many of the designs that we had are quite productive. They actually have lower energy of activation, which is kind of very cool because we never told this about the fitness function or something for the model to learn, but somehow it has actually captured some evolutionary details that tell it that this is the direction you want to go if you want to have better catalytic rate and so on. So one of the other things that also came out, which was a very cool observation, is the fact that from the experimental assays, just one round of it, we could demonstrate that we could get better at expressing enzymes. So out of the 96 designs that we tried, 89 of them expressed, and 48 of them actually have this malate dehydrogenase activity, which is like really high level of expressibility and also high level of like yield that you get per experiment. Now, what we are trying to do with this is to close the loop with respect to taking this experimental data that we got and feed it back to our generative model so that we can actually like generate new enzymes that have far more activity than what is found in the wild type. Now, you can ask why this is important. This is sort of important in many synthetic biology applications. For example, let's say you want to produce a medicine in the lab, or you want to say you want to produce some sort of a protein that is involved in like beer making. And again, beer making, textile making, all these actually use enzymes at very large scales, but they are usually restricted by the amount of production that they can get in the natural world. So a slowing step is essentially to design highly functioning enzymes that can still work, but not overtake the sort of population that they might have inside the bioreactors. So we are really pushing hard in terms of like saying, can we generate these new enzymes or generate designs of these new enzymes that we can rapidly evaluate in the lab and go forward? So this is one example where we can do this. Further addition to this is the fact that now I had this model suggest this experiment. I had this model suggest, how I should do this in terms of like running some, experiments as such. But we could basically ask the AI itself to do the experiment, right? So this is an example where the vision is essentially to start out with this very high level goal of saying, I want to design a protein that has this function. So for example, let's say I want to design a protein that can basically break carbon silicon bonds. Now you can ask why this is important. The carbon silicon bonds are something that is found in almost all electronics. So you want to basically get rid of them if you want to do like processing and recycling so that you can actually get more silicon on one side and carbon on the other side. This is not a bad idea, especially if you want to like do separation of these elements for like battery design and things like that, which can be used in a different line. But if I were to give this as my view, saying that I want to give the robot a high-level description of this hypothesis, and it basically enables you to continually work out what those experimental hypotheses should look like and either confirm or reject that hypothesis on the basis of what is given. So we basically are using AI and robotics and simulations to close the loop by planning, executing, and analyzing these experiments on the fly. So in fact, here is this virtual world that you see on the left-hand side. And the right-hand side, what you see is the actual implementation of it. Basically, this is a self-driving lab that does this experiment called as polymerase chain reaction. So this is a very baby step in terms of asking the robot to essentially learn how to do this protocol in the first place. And then I'm going to show you how the code was even generated by the AI to do this. But this basically builds on a lot of approaches towards planning, machine learning, and simulation to kind of design these experimental properties and outcomes that we care of, and automation of these experimental protocols at scale so that you can sort of do any design experiments in the lab without having to have human intervention. So there are like labs out there which talk about cloud labs where you have automation at much larger scales and so on. But what you might quickly realize is that the automation is actually enabled by humans, which is that the humans are always loading the samples. Humans are always bringing the instruments together to kind of achieve the experiments that you want to do. In this case, basically what you see here is that the experiment itself is kind of learned by the robot and then optimized for the set of equipment that we have in the lab. So this is a sort of application where you can have AI completely run end-to-end campaigns on the experimental side. And this is sort of linking a lot of the facilities that we have inside the lab. So for example, we are interested in designing new antimicrobial peptides. And in this case, we might have an antimicrobial that has to act on a new strain of bacteria that we might not even know what it is in the first place. So what you can do is I can go and say, I have all these peptide libraries that I have built up. I can query and understand what that peptide is actually like capable of. This is where one of the agents, as we call them, this is a large language model-based agent that can actually kind of synthesize new knowledge for you from ChatGPT and other sort of software to kind of get ideas on what these peptides might end up doing. You can then sort of identify what targets that those peptides might act on within the context of bacterial proteins. So you actually align the proteins, predict the structures, and you can sort of rank the structures on the basis of the results that you get, which tells us a lot about the function of these peptides and whether they might have action on these bacterial strains that we are interested in. And then once you do that, you can actually ask the BVBRC agent, which kind of tells you how to filter the results. Because if there is previous knowledge about the fact that this peptide acts very well, you can actually have that run on the same bacterial strain of interest and say, okay, I can get an answer for you very quickly. And so the first step is all driven by the AI in terms of formulating what that hypothesis might look like. The second set is basically agents that are built in order to run these HPC and AI resources, where I showed you an example of this ChatGPT-like app, which could go and design new enzymes. And then you generate these candidates for experimental evaluations where the self-driving lab performs these experiments and sends this back as part of the continuous feedback that